Good morning, everyone. Thanks for being here. And I'm Shuaiyu, a PhD student of University of Exeter. Today I will be talking about our work on a lightweight model for marine pollution detection. This method aims to improve the accuracy of detecting small and hard-to-spot pollution readings in the ocean. I combine both global context modeling and age information. Manipulations such as oil spills, floating garbage, or chemical waste directly harm to environments, shipping safety, and affect sustainable ocean use. To deal with this problem effectively, it's very important that we can detect pollution quickly and accurately using satellite images. But in practice, there are still some major challenges. As you can see, both datasets are heavily imbalanced. For example, in M4D dataset, almost 95 of the pixels are just the sea surface, where oil spill make up only about 2%. It's a similar story for the models dataset. Pollution classes are rare. Because of the imbalance, the model mostly learns to predict the majority class and often misses the small pollution region. On the right, you can see an example. In the middle, the model misclassifies the shape in the star images. We can see how repeated affect the age details. On the left is the original image with clear ages in the sand structures. After just one convolution, some age information is already become weak. You can see the main structures, but the small details start to fade. After two convolutions on the right, many ages are almost completely lost. This makes it harder to precisely locate the boundaries. This figure shows the differences in received field between standard convolution and selective scan. In the top row with standard convolution, each canal only looks at a small located neighborhood, but with the 2D selective scan, the received field extends much farther. The model can scan across both horizontal and vertical directions, capturing long-range dependencies. Inspired by above changes and advantages, we propose our EGMamba model, which combines several key components that I will explain next. The age-guided Mamba model includes three main blocks: wavelength Mamba encoder, age-guided attention, and the decoder. Wavelength Mamba encoder is our backbone that combines a state-space Mamba model with wavelength convolution to effectively enlarge the received field without adding too many parameters. Age-guided attention model extracts age information at multiple scales, helping the model focus more on object boundaries. In the decoder part, we apply channel-wise attention to better handle class imbalance and highlight important features, while still keeping skip connections to preserve spatial details. Next is the details of age-guided attention model, which is one of the core innovations in our design. The resulting age masks are then used to guide the attention block during feature fusion, ensuring that the important objects' boundaries are preserved during decoding. ablation study confirms that each module contributes significantly. The wave-light member encoder helps capture the global structure. The edge-guided block sharpens boundaries, and the dress decoder improves detection of small targets and fine features. Here we show how different loss functions affect the model's performance across categories. If we only use cross-entropy loss, as shown in the red line, the model perform well on the majority class, but struggle badly on minority class like oil spills and lookalikes. Our proposed combination improves both oil spill and lookalike performance while maintaining stability across all categories, giving us the highest mean insertion over unit. You can also see this visually on the right. The combined loss produce much cleaner segmentation. This shows that the model is quite sensitive to how we balance the loss function, and region awareness loss is critical to handle the server class imbalance in this task. When we apply our model on the M4D dataset, we achieve the state-of-the-art results. The oil spill insertion over unit improves by around 14% compared to the baseline, and the model makes the far fewer mistakes confusing oil spills with lookalikes. On the more complex models dataset, which has many more classes, our model still performs strongly, improving F1 score by about 4% over previous method, and currently segmenting multiple pollution categories under diverse conditions. Here we compare the confusion matrix of different models on the models dataset. On the left is a unit, in the middle is marine next, and on the right is our model. We can see that our model not only improves the overall segmentation performance, but also significantly reduces confusion between hard to distinguish pollution, which is exactly what we aim for in real-world marine pollution monitoring. Okay, so let's conclude my presentation. Thank you for your attention, and I'm happy to take any question.
Do you have any questions to ask Shuaiyu? Quick question. So when you detect the oil spills, which features you will focus more?
We need to focus more on the boundary, or as the different from the we can separate it from the sea surface.
So we know Mamba nowadays it's a popular one. Do you feel that it has any limitations in your research?
Sure. Due to the Mamba is not popular than the transformer, so we don't have the pre-trained models as the sea surface. So maybe we need to improve that.
Thank you. Next.